Hello, welcome to this lesson on conditional probability and Bayes' theorem. So this is a continuation of the previous lesson on probability. This is IT 1812 Mathematics OIT. We will first look at the learning outcomes. So by the end of this lesson, you should be able to compute conditional probabilities, apply conditional probability in real-world application, use the total probability theorem to compute the probability of an event. Use Bayes' theorem to compute probability of an event. So let's first look at conditional probability. Consider a sample space and two events A and B. So by now you understand what is meant by a sample space and the events A and B corresponding to sample space S. So it is sometimes of interest to know the probability of A given that the event B has already taken place. So this type of probability is called conditional probability of A given B. And it is denoted by this symbol P A given B. So you see a line between A and B. So that is how you denote conditional probability. So we properly define it formally. Definition 16.1. If B is an event with the probability of B not equal to 0 and A is an event, we define the conditional probability of P A given B as P A given B is equal to P A intersection B over PB. So in this case, we say that P A given B is the probability for A given B. So we straight away take an example. Suppose that the balanced die is tossed once. Find the probability of A given that an odd number was obtained. So the given part is odd number was obtained. So we approach the solution. We define an event A, observe a 1, and event B, observe an odd number. So we understand that since this is a balanced die, PA is 1 over 6. And PB of getting or observing an odd number is 1 over 2 or 0.5, right? Because we have three outcomes referring to odd numbers, 1, 3, and 5. So in this case, PA intersection B is equal to PA, which is 1 over 6. So now we calculate PA given B as PA intersection B over PB. So PA intersection B is 1 over 6 and PB is 1 over 2. And eventually, for the conditional probability of PA given B, you get 1 over 3. Okay, so moving on with the conditional probability for the independent events. So we come up with a definition, conditional probability and independent events. Two events A and B are said to be independent if any one of the following holds. That is, PA given B is equal to PA. And PB given A is equal to PB. And PA intersection B is equal to PA times PB. So we have seen this relationship, the third one, in the previous lesson. So we will go through an example. Consider the following events in the toss of a single die. Event A is observing an odd number. Event B is observing an even number. And we have an event C observing 1 or 2. So first question is deciding whether A and B are independent events. And next we have to decide whether A and C are independent events. So let's see how we approach this solution. So we have PA to be 1 over 2 and PB is 1 over 2 as well, because even and odd numbers, we have 3 even numbers, 3 odd numbers, total number of outcomes are 6. So that gives you PA is equal to PB is equal to 1 over 2. And PC, we understand that it's 2 of the 6 possible outcomes. That means PC is 1 over 3. So because we see that A intersection B is an empty set, right? A and B, because you can't experience odd and even numbers, odd number and an even number at the same time. Because of that reason, A intersection B is an empty set. There are no elements. Therefore, we see that PA given B is equal to 0. Okay, because the intersection part is null set and the probability of that is 0. Therefore, PA given B is not equal to PA, because we have a value for PA which is 1 over 2, 0.5. But PA given B, we see that it is 0. Therefore, we see that PA given B is not equal to PA. Because of that reason, events A and B are dependent. They are not independent. Now we have part B, where we have to look at events A and C. We can observe that A intersection C, that is observing an odd number and observing 1 or 2, they have something in common, right? So they have we have the in event C, we have the outcome of 1, which is which includes in event A. We can, as an odd number, we can experience the outcome 1. Because of that, PA intersection C is 1 over 6. Therefore, we can calculate PA given C to be 1 over 6 divided by 1 over 3, which gives us 1 over 2 or 0.5. Now we see that PA is also, the value is 1 over 2. Therefore, PA given C is equal to PA. Therefore, we can conclude events A and C are independent, because PA given C is equal to PA. Right. So these two parts, we have differing conditions. In the first instance, we had 2 dependent events. In the next incident, we had 2 independent events. So now with that, we move on to the multiplicative law of probability. So let's try to understand what this is. The probability of the intersection of 2 events, A and B, right? So PA intersection B is equal to PA times PB given A. Or in other words, we can write the other way, PA intersection B is equal to PB times PA given B. So this is the multiplicative law of probability. However, if A and B are independent, we see that PA intersection B is equal to the simple multiplication of probabilities of A and B, PA times PB. That's for the independent case, but otherwise you have to consider the more general multiplicative law, including the conditional probabilities. Now we introduce the law of total probability. Let's start with the formal definition. For some positive integer k, let's set b1, b2 until bk such that the sample space S is b1 union b2 union b3 and so on until bk. However, bi intersection bj with any combination is equal to empty set. Then the collection of sets b1, b2 until bk is said to be a partition of S. So we introduce the partition of the sample space before introducing the total probability. So next, move on to the theorem of total probability. Assuming that b1, b2 until Bk is a partition of S such that the probability of Bi for all I 1, 2 until K. Then for any event A, we can write PA equals to the summation from I equals 1 to K, PA given BI times PBI. So this is the relationship or the theorem of total probability. So for any event inside this sample space, you define the total probability of A as this relationship. Okay, we go through an example to understand. The completion of a construction job may be delayed because of a strike. The probabilities are 0.6 that there will be a strike, 0.85 that the construction job will be completed on time if there is no strike, and 0.35 that the construction job will be completed on time if there is a strike. So we are asked to calculate the probability that the construction job will be completed on time. Right, so let's see how we approach this. So we define event A as the construction job will be completed on time, and B is the event that there will be a strike. So in this case, PB, we know that it is 0.6, which is given. And we can write PA given B complement. What is B complement? B complement is job is not completed, construction is not completed on time, not completed, complement, right? So PA given B complement is 0.85, that is given. And PA given B is 0.35 because that is also given. Because the 0.35, the construction job will be completed on time if there is a strike. So that is the conditional probability, given that there is a strike. Okay, so how do we find the total probability of A? That is the probability of job completing on time. So we use the theorem of total probability. So PA is equal to PA given B times PB plus PA given B complement times PB complement. So you basically have to substitute the values for the conditional probabilities. You all have that, and also the PB and PB complement values. So with that, we can find out the ultimate probability for PA, which represents the construction job, probability of the construction job completing on time. Right, so now we introduce a very famous theorem in probability, which is Bayes' theorem. So this is related to conditional probability. So let us formally introduce it, assuming that B1, B2 until Pk is a partition of S such that PBI is greater than 0 for I is equal to 1, 2, 3 until K. Then the Bayes' theorem states P probability of Bj given A is equal to PA given Bj times PBj divided by the total probability, the summation of PA given BI times PBI. Okay, so this is the Bayes' theorem, and we will see how this is applied. We take an example for that course. There are, let's say, 5 students in this example, B1 to B5 in a class. A student randomly selected and a mathematical problem is given to him. The probability of B1 solving the problem is 0.2. The corresponding probabilities for B2, B3, B4, and B5 are given as 0.3, 0.4, 0.5, and 0.6 respectively. If it is given that the problem has been solved, find the probability that it is done by B1, one of the students called B1. Okay, so let's try to apply the Bayes theorem for this purpose. So let's start by defining the following events. BI is selecting student BI, and A is the problem has been solved. So we know that PB is 0.6, and PA given B complement is 0.85. And PA given B is 0.35 as it is provided. Now, so we know that PBI is equal to 1/5 for I is equal to 1, 2, 3, 4, 5 because we have 5 students. PBI is 1/5. There's an equal chance of students, one of the students having done it. And PA given B1 is 0.2. PA given B2 is 0.3 as it is given. PA given B3 and PA given B4, also PA given B5 is also provided. So therefore, after applying the total probability theorem, we can find out PA. Okay, so A is what the problem has been solved. So PA, what you do is to find out PA, you apply the total probability theorem, the summation of PA given PBI times PBI. And you can get the summation. You have all the values to substitute here. And when you do the calculation, you will arrive at 0.4 for PA, which is the probability that the problem has been solved. But it is not the requirement in this, that is not the value that we are asked to calculate in this example. What we require is PB1 given A. All right. Given that the problem has been solved, it is solved by student B1. So for this purpose, we need to apply Bayes theorem to define PB1A. And you apply the Bayes theorem as given here. So it will convert into PA given B1 times PB1. And you have to get the summation of PA given B1 BI times PBI. And now you have calculated all the required components to substitute in this equation, and you will ultimately get the value as 0.1 for PB1 given A. So this is how you apply Bayes theorem to solve a probability problem involving conditional probabilities. That brings us to the end of the lesson. So we have introduced conditional probability and Bayes theorem in this short lesson. In the next lesson, we will be addressing differentiation. We will conclude this lesson now. Thank you.